that much sense. That's mathematical taste, and I don't know how to teach it, and I bet you don't know how to program it.
Not yet.
It's not going to happen in my lifetime or in yours. Okay, now, first let me write this as a trigonometric.
Try a better marker.
I'm trying again. Let's try blue and see how it works. Hey! Now, you can take all 4 points close together, and so consider this as a circle with a very, very large radius, and let the radius go to infinity. And these points are going to come down to a line. So there's Ptolemy's theorem on a line. And Ptolemy's theorem on a line is a triviality. Let me hold off on that. I said I was going to give you the trigonometric form of it first, and then I'll come back to that. If this angle is alpha, beta, gamma, and delta, this one is beta because they cut off the same chord. This is alpha, this is delta, and this is gamma. And Ptolemy's theorem in trigonometric form says the sine of alpha plus gamma, which gives you this diagonal, times the sine of beta plus gamma, is the sine of alpha times the sine of beta plus the sine of gamma times the sine of delta. And alpha plus beta plus gamma plus delta is pi, and so this is pi minus alpha minus beta minus gamma. And the sine of pi minus x is the sine of x, so this is just sine of alpha plus beta plus gamma. Now, if you take beta plus gamma to be 90 degrees, this sine becomes 1, and you get the addition formula for the sine. If you take gamma to be pi over 2, then this thing becomes a cosine, and you get the addition formula for the cosine, and you can get the difference formulas also from this. So this contains the addition formulas, and it's a very nice problem to give to a course for prospective high school teachers. You get to this point, you give it to them for homework to try to prove this trigonometric identity. And we've done the addition formula. My favorite proof of the addition formula when I'm first teaching it is just to do areas. This angle A and B, the area is a half. AB times sine of A plus B, and it's the area of this triangle and this one, and that's the addition formula for the sine. You have to remember these formulas, you just remember the picture. Of course, you ought to know the addition formula for sine. And what do? They take and expand this out twice, and 3 pages later, the best of them might have a proof. But you want students to know that there are certain things of primary importance. The addition formulas for the trig functions, sine and cosine, maybe the tangent, are of primary importance. You need to know those backwards and forwards. Now, those are secondary importance, which you have to be able to get very rapidly from the things of primary importance. And one of them is the fact that sine of alpha times sine of beta is a half cosine of alpha minus beta minus cosine of alpha plus beta. When you just write down cosine alpha plus beta and cosine alpha minus beta and subtract them, you get twice the sine, product of the sines. And if you use that up here, the whole thing falls apart in one step. And we want high school teachers to know trigonometry well enough so that they wouldn't consider expanding this out when all you had to do is use this. And there are all sorts of proof of Ptolemy's theorem. One of them is to rationally parameterize a circle, take the unit circle and take a line with slope t, find this point, and you find that for 4 points then, and you compute the distances, and lo and behold, what you end up with is Ptolemy's theorem on a line, which is d minus b times c minus a equals d minus a times c minus b plus d minus c times b minus a. And that's a trivial linear identity to prove. And what I want to show you next, and I'm not going to go through the details, is what happens to Ptolemy's theorem when you have a general quadrilateral. Now this is almost certainly due to Bretschneider back in the 1840s. It's a long paper in German. My German is not great. And it's full of messy calculations. You know, when I say messy calculations. So I've never really read through the whole paper. But Ptolemy's theorem does exist for a general quadrilateral, but it has to include something else. And here's how you can prove it. You take 4 points, general position. Let me call them Z1, Z2, Z3, and Z4. We write down this identity. It's just a linear identity, so we can still write it down. Z3 minus Z1 and Z4 minus Z2 is Z4 minus Z1 times Z3 minus Z2 plus Z4 minus Z3 times Z2 minus Z1. And then you conjugate everything and multiply them together. And you get, well, when we multiply this by its conjugate, Z3 minus Z1 is just going to be x. So we get x squared. Z4 minus Z2 is y. We get that. When we do this, that's d squared, b squared. This is a squared, c squared. And then you have this term times the conjugate here plus this term times the conjugate here. And that turns out to be, well, they're conjugates of each other. A, B, C, D shows up. And then you have one of them, and you have to take the real part. And what you have to do is trace and see how the angles work out, and it turns out it's twice cosine of A plus C. Now, I know 2 proofs of this in the literature, in books, but neither one of them uses this complex variables proof. One of them uses, and this is in Hobson's book, basically the picture that we started off with for Ptolemy's theorem, except I didn't show you what Ptolemy's proof was. So let me sketch how Ptolemy's proof went. You take this angle and you construct another angle that's the same size there. And that big triangle up with this angle and this smaller triangle here with this angle are similar because these 2 angles are equal, because they cut off the same side. And then you write down what that tells you about the ratio of sides. And then you add that angle to each of these. And this triangle and the great big one here are similar because those 2 angles down here are the same and these 2 cut off the same arc, and you write down the same thing. And you can carry through that proof in the general case here when you have a convex quadrilateral by drawing in a line so that this angle and this one are the same, and this one and that one are the same. And then